Hello again. Today we're going to be looking at the derivative rules. So these are going to be rules that you'll need to memorize that will allow you to find derivatives without having to use the definition of the derivatives. Each one of these rules can be proved using the definition of the derivative, although I'm not going to go through the proof of every single one of these. These are just rules that you'll need to memorize, and they'll allow us to take derivatives really quickly in the future. So, first rule, simply the derivative of a constant is 0. And that's because the equation y equals a constant is a horizontal line. The slope of a horizontal line is 0 everywhere, and therefore the derivative is 0 everywhere. The derivative of x to the n times x to the n minus 1. So you bring down the power, then subtract 1 from the power. Important to do that in that order. This is the sum and difference rule combined just into one rule. The derivative of a function plus or minus another function. You just take the derivative of the first thing and then plus or minus the derivative of the second thing, assuming those two derivatives exist. Next rule is the constant multiple rule. If you have a constant k multiplied by a function, then the derivative is the constant, and then you take the derivative of the rest of it. Okay, so the way I like to think of it is the constant factors out of the derivative. Okay, these last two are the product rule and the quotient rule. So the derivative of a product of two functions, f and g, is the derivative of the first times the second plus the first times the derivative of the second. Finally, the quotient rule, the derivative of the top, or the derivative of a quotient, f over g, is the derivative of the top times the bottom minus the top times the derivative of the bottom all over the old bottom squared. Okay. I know these rules are probably not, well, they're definitely not familiar to you, but you do need to sit down and memorize them. But once you do, you'll be able to solve a wide range of problems. Now, these are not the only derivative rules. We will be getting more and more derivative rules as we talk about more types of functions. There are going to be rules for exponents, rules for logarithm, rules for the trig functions, and the inverse trig functions. Anyway, so with these rules right here, let's look at a couple of examples. Okay, so let's say that we have a table here that defines the value of f of x and g of x at x equals 1 and 2, and also gives us the value of the derivative of f and the derivative of g of x. Like that. Okay. And I want to find the derivative of h at 1 for h of x equals x squared f of x plus 2g of x. So I'm trying to solve for the derivative of h at 1, given that h is this function. Note, I'm not giving you exactly what f and g are, but this table should give us enough information to solve for the derivative of h at 1. Okay, so going through our derivative rules, I'm trying to take the derivative of this. This is a function plus another function. So I'm going to take the derivative of the first, and then plus, and then the second. Okay. So now I'm thinking, well, let's do it one little teeny step at a time. In the future, you should be able to apply these rules without going through as many tiny steps. But I think for now, let's put in a couple of intermediate steps. Okay, so there is just using the addition rule. Okay. Next, I want to take the derivative of x squared times f of x. Well, that's a product of two functions, so I'm going to have to apply the product rule. Okay. And to save space, I'm going to move up here. So the derivative of the first would be 2x times the second f of x plus the first, which is x squared, times the derivative of the second. So that is the product rule. Okay. And then plus the derivative of 2g of x, well, that's a constant multiple. So the constant multiple rule says that you just factor the constant out, and then you just have the derivative of g of x, which is just going to be g prime of x. Okay. Now that I have this, we can just plug in the number 1. So the derivative of h of 1 is going to be 2 times f of 1 plus 1 squared, which is just 1, times the derivative of f at 1 plus 2 times the derivative of g at 1. Great. Now we can just use this table. In fact, I'm only going to be using this column where x is 1. So f of 1 is 3. So this is 2 times 3 plus the derivative of f at 1 is 1. Then plus 2 times the derivative of g at 1 is minus 2. So this leaves us with 6 plus 1 minus 4, which is 3. So the derivative of h at 1 is 3. Okay, let's do one more example. This time we're going to find the derivative of h at 2 when h of x is x times f of x over g of x. Okay, so the main rule we'll be using is the quotient rule because the whole thing is a quotient. When we, in the middle of our quotient rule, we'll eventually have to take the derivative at the top, and then that will end up being a product rule. But the first outermost rule that we're using is the quotient rule. Okay, so we take the derivative of the top, so d dx of, and then the top is x times f of x, and then times the bottom, minus the top, times the derivative of the bottom, which is going to be g prime of x, and then all over the old bottom squared. In the next step, the derivative of x times f, well, that's a product rule, so that's a product, so use the product rule. So the derivative of the first is 1, because the derivative of x. The derivative of x, you might want to memorize as sort of like its own special rule. I mean, technically, x is x to the 1, and using our power rule, you'd bring down that power and reduce the power by 1, so you get 1x to the 0. And anything to the 0, well, as long as it's not 0 to the 0, but like 2 to the 0 is 1, 3 to the 0 is 1, so you just say that this is 1. It's a little bit, awkward to use the power of x rule for that, so it really is better just to memorize that the derivative of x by itself is always 1. Okay, so the derivative of the first is 1 times the second, then plus the first, which is x, times the derivative of the second, so the derivative of f. Now all of that is times g, so this needs to be inside of a parentheses, times g, and then minus x, f of x, g prime of x, all over x squared, or all over g of x squared. Okay. Now we simply plug in 2 and simplify it, and we're going to get our answer. Okay. So the derivative of h at 2 is going to be f of 2 plus 2 times the derivative of f at 2 in parentheses times g of 2 minus 2 times f of 2 times the derivative of g at 2 all over g at 2 squared. Okay, f of 2 is 1. And then the derivative of f at 2 is 7. Okay, g of 2 is 4. f of 2 is 1. The derivative of g at 2 is 0. And the derivative of g at 2 is 0. Well, that's, oh no, that's just regular g of 2. G of 2 is 4. Okay, good. Because we were about to divide by 0, but I was misreading my table. So no division by 0, that's good. Okay, 14 plus 1 is 15. 15 times 4 is 60. Divided by 4 squared, which is 16. Oh, by the way, that went to 0. So we're just left with 60 over 16. Let's see, we could simplify that by dividing by 4 on top and bottom, leaving 15/4. So the derivative of g at 2 is 15 over 4. Okay, I think I have one last example that I'd like to do. Yep. This is going to be a sort of a real world example, like a word problem. So the population in tens of thousands of squirrels on UT campus is given by P of t equals t plus 20 over t squared plus 400, where t equals 0 in the year 2000. Find and interpret P of 0, P of 20, the derivative of P at 0, and the derivative of P at 20. Okay, so the first two are just plugging in 0 and 20. So let's see what that is. P of 0, if you just plug in 0, you get 20 over 400. Which simplifies to be 2 over 40, or 1 over 20, which is 0.05. But this population, I stated at the start, is in tens of thousands of squirrels. So 0.05 times 10,000 ends up being 500. So this translates to 500 squirrels. And this was time equals 0, and time equals 0 was in the year 2000. So we had 500 squirrels in the year 2000. So that's the interpretation of what P of 0 equals 0.05 actually means. 500 squirrels in the year 2000. Okay, so if we plug in 20, we would get 20 plus 20 is 40 on top. 20 squared is 400, plus another 400 is 800. We get 40 over 800, which is also 1 over 20, which is still 0.05, so still 500 squirrels. So it turns out that when t equals 20, that's 20 years after, oh, did I say in years? Sorry, I forgot to explain that t is in years. T is in years, and that t equals 0 is the year 2000. Therefore, t equals 20 would be the year 2020. So P of 20 would mean that you have 500 squirrels in the year 2020. So just a coincidence that the year 2000 and the year 2020, we both have the same number of squirrels, 500. Okay, the last two things is to find and interpret the derivative of P at 0 and the derivative of P at 20. So first we need to find the derivative function. And to do that, we've got a quotient, so we must apply the quotient rule. So the derivative of the top is 1 times the bottom, t squared plus 400, minus the top, which is t plus 20, times the derivative of the bottom, which is 2t, and then all over the old denominator squared. And I'm just going to leave it like that. Okay. Next, what is the derivative of p at 0? So if we simply plug in 0 for t, notice that this is 0, and 0 times anything is 0. So this part goes away completely, which is nice. And 0 here makes the numerator go to 400. The denominator is 400 squared. So 400 divided by 400 squared is 1 over 400, which is, let's see, 100th would be 0.01 and then divide by 4. So 0.0025. Okay. And then we need to interpret this. Okay. The derivative of p at 0 is the rate of change of the population with respect to time. And remember, populations in tens of thousands, so we need to once again multiply this by 10,000. So that would be shifting the decimal place 4 places to the left, which would give you exactly 25. So this means that 25 squirrels per year, that's the rate at which the population's growing. So in the year 2000, the squirrel population is increasing by 25 squirrels per year. And I believe our population was 500. So that might mean that we might estimate that our squirrels in the year 2001 would be approximately 500 plus another 25, or 525. Okay, next let's look at the derivative of p at 20. Okay, 20 squared is 400 plus another 400 is 800. And then minus 40 times another 40 is 1600. The denominator would give us 400 plus 400 is 800 squared. We wind up with a negative 800 over 800 squared, which is negative 1 over 800. Okay, that's 0.00125. Oh, negative. And then if we multiply that by 10,000 by shifting the decimal place 4 places to the right, that would be negative 12.5, which means that our population of squirrels in the year 2020 is decreasing, because of the negative, by 12.5 squirrels per year. So even though the two populations were equal in the year 2000 and the year 2020, it turns out that the population is increasing or growing in the year 2000, where our squirrel population is now decreasing in the year 2020. So the graph must have been going up, and then now it's going down, if we were to look at the graph of this function. Anyway, so that's the last problem for today. We will be learning more derivative rules, because like I said, those rules that we had are fine for like taking derivatives of like polynomials or rational functions, a polynomial over a polynomial. But we really need more rules to learn how to handle exponents, logarithms, trig functions, inverse trig functions, and also composition of functions, which is when you put one function inside of another function. So those rules we'll be learning in the next week or two. Anyway, that's going to be it for today's video. Hope you have a good day.